I would like to say hello to everyone. I'm Parham Sadeghi and I will be presenting here my paper, a new analytical simulator for the provisioning stage of IoT-based WSNs. First, there will be an introduction. I will go through related works briefly and then explain the methodology and experimental setup and evaluation. Finally, I will conclude this paper. First off, what is IoT? IoT is a set of connected devices aimed at information acquisition, data processing, and services based on that data. Such IoT devices are becoming ever more present in our everyday lives, and more applications seem to be developing for these devices. These efforts are done to realize the dream of ubiquitous connectivity and seamless connection. Although comprised of inexpensive devices and boasted as the means of money saving in the long run, such deployments can be expensive at first due to deployment procedures that ensue the initial inception. These steps in turn include inception, service definition, feasibility analysis, provisioning, prototyping, and debugging. Usually, the feasibility analysis, provisioning, and parts of the prototyping are done using a simulator to save on costs. But the simulators themselves have evolved over time and are now usually huge software structures that require expertise themselves. And aside from some of the paid simulators, that expertise itself incurs a lot of costs. Not much of an issue in traditional networks, but they make up a good portion of the cost for IoT applications, and should an idea fail the feasibility test or the provisioning stage, they make up all the costs. This is besides the time spent during this phase, which would have been better spent in prototyping and debugging to offer a more robust solution or add more initial features. So, sometimes a quick and dirty simulator is preferred to such cases, and as a result, we propose a modular analytical simulator. Our proposed simulator incorporates models for the channel, physical layer, MAC layer, 6-loop compatibility layer, and utilities needed for topology creation, environmental parameter inputs, routing, and routing metrics. All of this can be changed to suit the user. The point of simulation is to use the computer to predict the evolution of a given system through time in order to study it. Three main forms of simulation are time-based, event-based, and analytical. Time-based simulation is mostly used when studying a natural phenomenon, while event-based simulation is mostly done when man-made processes are under consideration, like computer networks or manufacturing processes. Analytical simulation is used to study both, and like any other method, comes with its own set of advantages and drawbacks. Channel model and modulation. There exists an enormous body of research in this area. Models range in accuracy from simple disk models used in higher-level simulators interested in the effects of other layers, like routing or application, to ray-traced Rayleigh models. Almost all of these models contain an empirical part, which is obtained under different scenarios and plays an important part in models' accuracy. MAC layer. At this point in time, using a 2D discrete Markov chain is the standard practice when it comes to modeling CSMA mechanisms. This model was first used on IEEE's 802.11 Wi-Fi and was later expanded upon for other MAC protocols. These models have been continuing to enhanced upon by data from other methods, such as collision neighborhoods, which is used to enhance the accuracy of our model. Network layer and routing. No complete analytical models exist for network layer and routing of IoT networks. There have been efforts using Markov chains and game theory to model them, but the bulk of the effort is in extending the models that already exist. Methodology. Our simulator is built on the philosophy of modularity. This simulator is made up of different modules for different parts of the network, which can be swiped out for other applications. These modules are explained in the following slides. Channel model. Our simulator supports two different channel models. First is a simple disk model, and the second one, or the more accurate one, is a log-normal path loss model with Gaussian shadowing, as shown in the equation below. This model was first developed to predict signal behavior in the transitional regions of cellular networks, but is applicable almost everywhere and the values have been changed to better reflect the effects of our deployment. As you can see, the path loss for the distance d is given in decibels. d0 is the reference distance of 1 meter, eta is the path loss exponent, which is an empirical value, chi is a Gaussian random variable to model noise, and sigma is its standard deviation. Physical layer. IEEE's 802.15.4 supports many modulation and encoding schemes. The effects of these mechanisms along with the channel is summarized in the parameter R5. Among those, the simulator supports GFSK, BPSK, and OQPSK. The DSSS is not supported as it violates the inexpensive mindset of IoT and is usually not used. Although an RZ is the encoding scheme used by 6LoWPAN, the simulator supports other coding schemes as per IEEE 802.15.4's physical layer specification. MAC layer. The CSMA mechanism of the MAC layer is unsurprisingly modeled by a 2D DTMC. The steady-state probabilities of this chain are calculated along with the equations from the collision neighborhood to find its reliability, Rmac. This value denotes the probability of sending a packet fully and without collision. It depends on many parameters such as number of neighbors, the packet generation rate, and packet length. On to routing. The RPL routing protocol of 6LoWPAN uses two metric functions in order to find the best path to sync. First one is a simple hop count based function, and the other one is based on ETX. The simulator presented here supports both objective functions and can be easily expanded to support different ones. The original ETX uses the transmission of multiple packets to find the link's reliability. We calculate their reliability using the formula provided here, with the reliabilities calculated before. Network layer. IP version 6 cannot be directly run on most nodes used in IoT applications, so the 6LoWPAN compatibility layer uses mechanisms to compress the lengthy IP version 6 header and handles the fragmentation of packets. Older versions of this standard use mesh underrouting, which uses the MAC layer routing protocol to send the fragmented packets, where they are first fragmented at the source and then put back together at the destination. Newer versions of this standard uses the route over mechanism, where fragments are reassembled at each intermediary node. Although this might seem like a waste of effort, this does in fact make reliability go much higher than the mesh under mechanism for fragmented packets. Analytical models of both of these mechanisms are shown here. MAC max frame retries is a parameter of MAC layer protocol and is usually between 3 and 5. We have taken it to be 5 in our simulator. F is the number of fragmented packets, and R bar denotes the average reliability of the links in our path. Experimental setup and evaluation. Our proposed simulator here was compared against the well-established IoT simulator Kuja in two scenarios. Nodes are dispersed on an XY grid with 5-meter intervals, and the packet generation rate for each node is 1.2 packets per minute. The environmental parameters for the analytical simulator are given in the table here. We have set them to be as close as possible to real life and the simulator Kuja. For simulated results, each scenario was allowed 30 minutes of simulated time from the start of simulation for the network to converge. The results were then obtained for a duration of 2 hours of simulated time. The package length was 200 bytes in order to be fragmented into two parts, and the nodes were working in the 2.5 GHz range of the IEEE 802.15.4. Our first scenario. The topology depicted here is of a more centralized nature. This was chosen as it more closely represents modern IoT deployments, where nodes are closer to the sink. Nodes being closer to the sink causes the MAC layer to play a much more important role in the overall reliability of the network. The results for the ETX value is shown in this graph, And as mentioned, because the MAC layer plays much more important role here, the results are very, very close. This table shows each node's reliability when sending packets to the sink. The results are shown for both analytical and simulated results and for both mechanisms of the route over and mesh under. Our second scenario. This scenario is representative of traditional WSN applications that are implemented using IoT standards and 6LoWPAN. The topology is depicted in this figure and its multi-hop nature is evident. Values for each link's ETX is shown here in this graph. There is a wider range due to the highly stochastic nature of this network. The results for each node's reliability when sending to sink are represented in this table. As the network depth increases, so do the higher order effects of the stochastic behaviors talked about. Nevertheless, the results are still on the same scale and good enough for feasibility analysis, as results from Kuja simulator itself fall under the error margin, with such small and close numbers. A significant remark should be made concerning these results. Where the analytical simulator's results were ready in a matter of seconds, it took the simulator hours to generate these results, and the difference of timescale can only increase with larger and more sophisticated networks. This is the actual advantage of an analytical simulator as compared to an event-based simulator. In this paper, an analytical simulator was proposed to ease the provisioning stage of IoT-based WSN deployments and their feasibility analysis. The tool with its analytical models were validated along with the simulation data obtained from Kuja Simulator, which is the most widely used tool for these jobs. We hope to further enhance this simulator with models for Contiki MAC and the slotted version of IEEE's 802.15.4, as they may come in handy in future cases. Thank you.